Hello, welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. All right. So far we have looked at how to compute the MMSE or the minimum mean squared error estimate when the parameter and the observation are jointly Gaussian. All right. So now let us look at an application of that principle in the context of a wireless sensor network. Okay. So what we want to do today is we want to look at an application of the MMSE estimation. All right. So, an application, we want to look at an application of the MMSE estimation principle in the context of a wireless sensor network. So, all right. Okay. So, we want to look at an example of MMSE in the context of a wireless sensor network or WSN. Now, what we have in a wireless sensor network, we have already seen a model for this. What we have is we have several sensor nodes which are communicating with a fusion center. So, we have several sensor nodes. For instance, this is a sensor node, but typically we do not have a single sensor node, but rather we have several sensor nodes which are communicating or sending their. So, all these are small circles are the sensor nodes which are sending their measurements to a fusion center, or what is known as in a wireless sensor network, this is also known as a cluster head, which is basically cluster head means it is the head node of this cluster of sensor nodes. Fusion center means it is basically the center which fuses the measurements from the different sensor nodes. All right. So, this is also known as a fusion center in the signal processing context. In a networking context, this is also known as a cluster head of the wireless sensor network. Okay. So, now what is the idea? This is a schematic diagram. So, what is this? This is a schematic diagram of a wireless sensor network. Wireless sensor network, which we are abbreviating by WSN. Remember when, okay, this is the abbreviation WSN for a wireless sensor network. We have a schematic diagram of the wireless sensor network. Okay. What these different sensor nodes are doing are, these are basically trying to measure a parameter h. So, consider the measurement of parameter. This parameter we are going to denote by h. Okay. So, that is our parameter. Okay. And this parameter can be anything. For instance, in a wireless sensor network, typically you measure parameters such as the temperature, okay, or the pressure, okay, can be anything, pressure, or for instance, for that matter, the humidity. Okay. Wireless sensor networks have several applications, all right. So, the moisture content of the soil and so on. So, there are several applications where wireless sensor networks can be used, such as agriculture, weather monitoring, etc. So, there are different parameters one can measure, the temperature, pressure, etc. So, h denotes the parameter. So, we are denoting by h the parameter that is being measured, all right. Now, each sensor makes a measurement. Obviously, that measurement is going to be noisy, all right. That is the whole point of estimation, because you have noisy measurements or noisy observations, all right. So, we have the observation, let us say at kth sensor, we have yk equals the parameter h plus vk. So, we have the parameter, you have your parameter, and then you also have Vk, which is your noise, which we are going to assume as Gaussian with mean 0, variance equals sigma square, which means basically expected mean 0 means basically your expected value of Vk equals 0, variance equals sigma square means basically expected value of V square k, since we are considering real parameters or real noise. If it is complex, then we have to write expected value of magnitude V square k, sorry, that is not 0, that is basically your sigma square. Okay. Now, h is the parameter. Now, in this context, we are going to assume h is a Bayesian parameter, that is a random parameter. Remember, there are two different settings. This is the Bayesian MMSE setting. Therefore, the parameter h is random in nature. More specifically, in this context, since we are considering a Gaussian estimation scenario, we can consider the parameter h to be Gaussian with a certain mean and a certain variance, which I am going to shortly write down. Okay. So, h is a Gaussian parameter, very simple, this is a Gaussian parameter, everything is Gaussian. So, this is a Gaussian parameter with expected value of h equals mu h, expected value of h minus mu h square equals sigma h square. Okay. So, mu h, what is this? This is basically the mean of the parameter, and what is this? This is the variance of mean of the parameter, and this is the variance of the parameter. Okay. So, now what we have done, we have modeled a single measurement, this yk, we have not written this down, this yk, this is your measurement. Okay. Okay. Now, what we have is we have a measurement yk equals h, the parameter, plus noise Vk, but of course, we will not have a single measurement, rather we will have a group of n measurements, that is y from the, because we have n sensors, let us say, correct. In a sensor network, we have many sensors, alright. So, let us say we have n sensors, therefore, naturally we will have n measurements. Okay. So, we consider a WSN with capital N sensors, which implies that there are n measurements. Okay. So, the n measurements can be denoted as y1 equals h plus v1, y2 equals h plus v2, so on yn equals h plus Vn. Okay. So, these are your n measurements. Okay. So, these are your n measurements. Okay. N measurements of the same parameter, mind you, that is important to keep in mind. These are n measurements of the same parameter, right. So, you have multiple measurements of the same parameter from which you are trying to estimate this parameter h. Obviously, as the number of measurements increases, we expect the estimate of the parameter to improve, right. If you take more and more measurements, all right, that means we expect by using these by using this larger number of measurements, we expect to improve the estimation accuracy. Naturally, that is the point behind taking more measurements, or that is the point in fact behind having a large number of sensors in the wireless sensor network. Okay. So, one has to keep that in mind. Okay. So, now we have, I can write this in the form of a vector, your observation vector y1, y2, so on up to yn. This is your observation vector, this is equal to the vector of all ones. Okay, this is equal to the vector of all ones times h plus the noise vector. Okay, v1, the vectors are n dimensional naturally, because you have n sensors and n measurements. So, this is now your observation vector, this is your vector of all ones, which we are going to denote by 1 bar. This is the vector of all, this is the vector of all ones, and this is your, this is basically your noise vector. Okay. This is V bar, which is your, this is V bar, which is your noise vector. Okay. This is the noise vector. Okay. That is fine. Now, let us look at this. Now, V bar is Gaussian because the noise samples are Gaussian. So, V bar, let us denote this by, this is let us say V bar. So, if we can write this model, we can write this. Now, naturally this is your observation vector, that is Y bar. So, I can write Y bar equals 1 bar times H plus V bar. Now, look at this, this is a Gaussian vector, this is a Gaussian parameter, all right, that is what we have assumed. Okay. And therefore, now if you look into it, this is parameter H is Gaussian, vector V bar is Gaussian, you are adding two Gaussian quantities, therefore, the output Y bar, that is also Gaussian, all right, because of the property of the Gaussian random variable, when you add two Gaussian random variables, you get another Gaussian random variable, all right. So, the output observation vector Y bar, that is also a Gaussian vector. Okay. So, this is a Gaussian vector. So, now we have a scenario in which the observation is Gaussian, that is Y bar, the observation vector is Gaussian, the parameter H is also Gaussian, therefore, now I can use the MMSE theory developed so far of estimating the Gaussian parameter H from the Gaussian observation vector Y bar. Okay. So, that is what I am going to do. Before that, we are going to characterize the noise, and this is important. I am going to assume the noise is basically, we already said the noise is 0 mean. We are going to assume the noise samples V1, V2, Vn, and this is going to be an assumption we are going to often use. V1, V2, Vn, we are going to assume that these are IID Gaussian, where IID stands for independent identically distributed. This is independent identically distributed Gaussian. What do we mean by that? We mean that each V1, V2, Vn are Gaussian, all right. Now, also they are identical, which means expected value of each Vi or Vk is 0, expected value of Vk square is sigma square, that is what we already seen. And further, these different V's are independent, which means expected value, that is if I look at expected value of Vk into Vl, since they are independent, this will be equal to expected value of Vk times expected value of Vl. So, this is 0, this is 0. So, therefore, this is equal to 0, but mind you, if k is not equal to L, all right. So, expected value of Vk into Vl is 0 if k is not equal to L. Of course, if k is equal to L, this becomes expected value of Vk square, which is sigma square, that we already know, that is expected value of each Vk, the mean is 0 and expected value of V square k equals sigma square. Therefore, if we look at the covariance matrix of this noise, now what we want to look at is the noise covariance. matrix. And what is this? This is simply expected value of V bar transpose, which is equal to your expected value of, now I am going to write V bar is your vector V1, V2, Vn times the vector V transpose, which is column vector transpose is row vector Vn. Okay. Now, I can simplify this. If you can see, if you now multiply this column vector by row vector, what you will get is you will get expected value of V square 1 on the diagonal, you will get all the square elements V square 1, V square 2, so on up to V square. On the off diagonal, you have V1, V2, you have V2, V1. Now, you can see if I take the expectation operator inside, all these elements are the diagonal elements, expected value of V square 1, V square 2, so on, these are sigma square. All the off diagonal elements V1, V2, these are 0, all right, if you take the expectation operator inside. And therefore, what I have is the covariance matrix. If I look at this, that is sigma square, sigma square, sigma square, and the off diagonal elements are 0. So, basically this becomes sigma square times the identity, and more specifically times the n cross n identity matrix. Okay. This is what is this? This is the covariance matrix of the noise vector V bar, that is expected value of V bar transpose, this is equal to sigma square times identity. This we already said is the covariance matrix . This is the covariance matrix of the noise vector. Okay. Now, further we are going to make another interesting and important observation, which is also very natural and logical, that is, we are going to assume that the noise vector V bar and the parameter are independent or basically uncorrelated. Now, of course, since they are both Gaussian, uncorrelated also implies independence. One implies the other, that is, uncorrelated implies independence and independence implies uncorrelated, because it is Gaussian, all right. So, and this is also logical because the parameter comes from the environment, all right. This is based on, for instance, if you are trying to sense the pressure or temperature or so on, and the noise, all right, the noise is basically the noise, the measurement noise which arises because of the thermal noise in the sensor equipment at the sensor nodes and so on. So, it is logical to assume that these two quantities, the noise, all right, the noise and the parameter that are being sensed are independent, because these arise from totally different effects, one can say, all right. So, the parameter h, okay. So, we have the parameter h. So, we have expected, remember, h minus mu h times V bar transpose, this is the parameter, minus, of course, you are subtracting the mean. This is your noise vector. So, the parameter and noise vector are uncorrelated. That is the important assumption that we are making, which is also, as we said, logical. Parameter and noise vector are actually they are independent, but here uncorrelated suffices because they are both Gaussian. So, naturally, if they are uncorrelated, it follows that they are independent, okay, they are one and the same. Okay. So, for that we are just going to say that they are uncorrelated, which means the expected value, that is the covariance expected value of h minus mu h times V bar transpose, that is equal to 0. Okay. So, this is basically the framework of estimation, parameter estimation in wireless sensor network. All right. So, now let us proceed towards estimation of the parameter h from the observations y1, y2 up to yn, that is our ultimate aim. Okay. So, now what we have, let us first compute, we have y bar equals 1 bar h plus v bar. So, let us now proceed towards estimation. So, I can calculate the expected value of y bar as the expected value of 1 bar h, sorry not h bar, 1 bar h plus v bar, which is equal to, of course, 1 bar is a constant, 1 bar times expected value of the parameter h plus expected value of v bar. Now, this we know expected value of h is mu h. Now, this we know is 0, expected value of. So, we have expected value of y bar is expected value of 1 bar h plus v bar, which is equal to 1 bar into expected value of h, that is mu h, plus expected value of v bar, which is 0, because each expected value of the mean of each noise element is 0. So, it follows that expected value of y bar equals 1 bar times mu of h. So, the mean of the observation vector equals 1 bar times mu of h. Okay. Now, we want to find r y y, remember, because that is the another quantity we need in the MMSE estimation, that is expected value of y bar minus mu y bar times expected value of y bar minus mu y bar transpose, that is r y y, that is the covariance matrix of the vector y bar. Okay. So, we need expected value of y bar minus mu bar y. Okay. This is, you can say, as the mean of y bar times y bar minus mu bar y transpose. What is this? This is the covariance. Okay, this is, let me write it properly, this is the covariance matrix of the observation vector y bar. This is also denoted by, if you remember our notation, also denoted by capital R y y, which is equal to, now let us substitute this. First, let us look at this quantity y bar minus mu bar y, that is equal to y bar is 1 bar h plus v bar minus mu bar y, the mean of the vector, which is 1 bar mu of h, correct. That is what we have derived. Mu bar y is 1 bar mu of h. So, I have 1 bar into h minus mu of h plus v bar. Okay. So, this is your quantity y bar minus mu bar y. Now, therefore, expected value of y bar minus mu bar y into y bar, it is slightly messy, but it is fairly easy actually to derive this thing. That is equal to, I just have to substitute this terms, expected value of y bar minus mu bar y is 1 bar h minus mu of h plus v bar into the product 1 bar h minus mu h plus v bar transpose. Now, this is going to be equal to, this is equal to what we have over here. This is now, if I expand this, let me write one more step, 1 bar into h minus mu of h plus v bar times transpose is h minus, of course, this is a scalar quantity. So, it does not matter, h minus mu of h into 1 bar transpose plus v bar transpose. Now, if you multiply term by term, what you are going to get is expected value of, let us look at the first term, h minus mu h square, h minus mu h square times 1 bar transpose. Of course, we know this is sigma h square, plus if you take the last two terms, then you have expected value of V bar transpose. This we know is sigma square identity. Now, it remains to look at the cross terms, that is the terms in the middle, that is plus expected value of what we have h minus mu h into V bar into, or we have 1 bar into x minus mu h into V bar transpose. Of course, we know that the noise and the parameter are uncorrelated, this is equal to 0 plus expected value of V bar into h minus mu h into 1 bar transpose. Of course, we know that the noise and the parameter are uncorrelated. So, this is again, this expectation is again 0. So, what we are left with is basically finally, we are left with only the first two terms, that is sigma h square times 1 bar into 1 bar transpose plus sigma square identity, where sigma square is the noise variance. Sigma square, remember, is the variance of each noise sample. This is the noise variance. This is the parameter prior variance of the Gaussian parameter. Okay, sigma h square. So, this is what, this is my RYY, which is observation covariance. In fact, it is a covariance matrix of the observation vector RYY, which is expected value of y bar minus mu bar y into y bar minus mu bar y transpose, which is equal to sigma h square times 1 bar transpose plus sigma square times the identity matrix. Okay. Now, we want to derive the next quantity that we need is the cross covariance, that is expected value of h minus mu h times, right, y bar minus mu bar y transpose. This is equal to r h comma y. This is the cross covariance between the parameter and the observation. Now, what we can do here is we have h minus mu h, that we have anyway, y bar minus mu y bar, this is 1 bar into h minus mu h. Remember, y bar minus mu y bar is 1 bar into h minus mu h plus v bar transpose of this quantity, that is equal to expected value of h minus mu h times, of course, now I have to take the transpose of this quantity, 1 bar transpose into h minus mu h plus v bar transpose. H minus mu h is a scalar, that is why I have not, I can just let it remain where it is, which is equal to expected value of, now split it into the components, expected value of h minus mu h square into 1 bar transpose plus expected value of h minus mu h into v bar transpose. We know this is equal to 0 because the noise and the parameter are uncorrelated, while this we know not this, well, this quantity expected value of h minus mu h square, this is sigma h square. So, therefore, this net quantity, if you can now look at this, which is also very simple, again nothing very complicated, this is sigma h square into 1 bar transpose, which is r h y. Okay. And therefore, now the MMSE estimate, remember MMSE estimate, now we have r h y, we have r h a, r y y, the MMSE estimate is given as, recall that the MMSE estimate equals RHY cross covariance times RYY inverse times y bar minus mu bar y plus mu h, okay. And we know each of these quantities RHY we have calculated is 1 bar transpose times sigma h square, RYY is basically we have calculated that as sigma h square into 1 bar transpose plus sigma square identity inverse into y bar minus mu y bar is 1 bar into mu h plus mu h. Okay. Let me just write it a little bit more clearly. This is equal to 1 bar transpose sigma h square 1 bar transpose plus sigma square identity inverse into y bar minus 1 bar into mu h plus mu of h. And what is this? This is therefore the MMSE. Now, what we have is we have a neat expression for the MMSE estimate of we have an expression for the minimum mean squared error estimate of the parameter h. So, what we have done in this module is in something interesting. We have looked at how to use this principle of MMSE estimation in the context of a wireless sensor network. We have considered a wireless sensor network with n sensors making n measurements y1, y2 up to yn. The parameter h, which is let us say any parameter that is either the temperature or pressure so on, is assumed to be Gaussian in nature in the presence of Gaussian noise. Therefore, the observations are also Gaussian. Now, from this Gaussian vector we estimate this Gaussian with Gaussian parameter h, we calculated the covariance matrix of the observation vector, we calculate the cross covariance between the observation and the parameter, and now we have developed the MMSE, that is the minimum mean squared error estimate of this Gaussian parameter h in the wireless sensor network. Now, if you notice, this expression is slightly unwieldy, all right, it is slightly messy, it is a long expression. What we are going to do in the next module is to develop to simplify this further and develop a nice intuitive a nice more simplistic expression, and also which conveys more meaning, also which yields a lot of intuition. All right, thank you, thanks very much.